I'm using a technique called kernel approximation to speed up calculations. Specifically, I'm using the SkewedChi2Sampler, which is good for data that's not evenly distributed. I have a dataset with 1,000 different entries, and each entry has 5 different pieces of information. I'm setting the NCOMPONENTS parameter of the SkewedChi2Sampler to 100. This means I want to create 100 new features from the existing 5. Think of it like creating more detailed descriptions from a simpler set. I'm asking you to evaluate the effects of my choice to use 100 new features. If I increase the number of new features, I'll get a better approximation, but it will take longer to compute. It's a trade-off. The new features I create won't be totally unrelated. They are connected by the original data. The SkewedChi2Sampler is somewhat tolerant of uneven scales in the original data, but ideally I should still pre-process my data for best results. I won't get a perfect copy of the original data structure. There will always be some level of information loss since this is an approximation. I see this statement as false. Although the SkewedChi2Sampler works well with skewed data, it doesn't automatically adjust for features with different scales. To get the best results, you should usually scale your features first, for example, using standardization. Think of it like this: if you're measuring distances in both miles and kilometers, you'll need to convert everything to the same unit for fair comparison. Similarly, features on different scales need to be normalized before using the SkewedChi2Sampler for accurate approximation. This statement is false. The SkewedChi2Sampler doesn't create completely independent features. The generated features are connected through the original data and the approximation method. Think about making a summary of a long story. While the summary is shorter, the different parts of it are still related to the original storyline. Similarly, the created features are related, they're not isolated pieces of information. I find this statement false. Kernel approximation is, by nature, an approximation. It's like making a rough sketch. You capture the essence, but not every detail. You'll always have some information loss. A perfect reconstruction wouldn't be an approximation. I'm using a technique called kernel approximation. It's like creating a shortcut to make a complex calculation much faster. The SkewedChi2Sampler is a specific tool within this technique, especially good for data that's not evenly distributed. Think of it like finding a quicker route on a map instead of driving the long way around. Cool, huh? I have a dataset. It contains information about 1,000 different things, samples, and each thing has 5 different characteristics, features. For instance, the samples could be houses, and the features could be size, price, number of bedrooms, number of bathrooms, and lot size. The NCOMPONENTS parameter controls how many new features I create. I set it to 100, which means my kernel approximation technique will generate 100 brand new features from the original 5. Think of it as taking 5 ingredients and creating 100 different dishes from those original ingredients. This is the data I feed into my SkewedChi2Sampler. I am using the same dataset mentioned previously. The result of my kernel approximation is 100 new features which are, well, approximations of the original relationships in the data. These approximations give me the same information with less computational power. It's a smart way to simplify calculations without losing too much information. Pretty neat, right? I'm using scikit-learn's kernelapproximation with the SkewedChi2Sampler to make a faster, simpler version of a complex kernel function. Think of it like creating a quick sketch instead of painting a highly detailed masterpiece. I have 1,000 different data points, each described by 5 characteristics or features. For example, imagine each data point is a house, and the 5 features describe its size, number of bedrooms, location, age, and price. I'm using SkewedChi2Sampler, a special tool to approximate the kernel. NCOMPONENTS equals 100 means I'll create 100 new features from my original 5. The SkewedChi2Sampler will generate 100 new features from my 5 original ones. Each new feature is a combination of the original features, designed to capture the relationships within the data more efficiently, much like creating a summary of a large text. Increasing the number of new features, higher NCOMPONENTS, generally improves the approximation's accuracy but also increases the computational cost. More features mean more calculation, like trying to solve a more complex puzzle. The new 100 features won't be completely independent of each other. They are related because they come from the same original 5 features. It's like having siblings, they're related, but not identical. SkewedChi2Sampler doesn't automatically adjust for features with different scales. Think of measuring house size in square feet and price in dollars. Those have very different scales. It's best to scale them before using SkewedChi2Sampler. The new features will not perfectly recreate the original data's relationships. It's an approximation, similar to summarizing a movie plot versus watching the entire movie. I'm using a technique called kernel approximation from the Sklearn library. Specifically, I'm using the SkewedChi2Sampler to make a faster, simpler version of a kernel function. Think of it like creating a shortcut for a complex calculation. I have 1,000 different data points, each described by 5 different characteristics or features. For example, imagine each data point is a person, and the 5 features could be height, weight, age, income, and shoe size. Using the SkewedChi2Sampler, I will generate 100 new features from my original 5. These new features are approximations derived from the original ones, aiming to capture the important information more efficiently. The SkewedChi2Sampler is the tool doing the approximation. The _n_component's parameter is set to 100. This means that the method will create 100 new features. A higher number generally means a better approximation, but it also increases the computation time. I'm using Sklearn's kernelapproximation tool with the SkewedChi2Sampler to approximate a kernel's feature map. Think of it like creating a simplified, faster stand-in for a complex calculation. I have a dataset, 1,000 individual examples, each described by 5 different characteristics. This is my starting point. The SkewedChi2Sampler is the specific tool I use to do the approximation. The _n_component's parameter is set to 100. This means I'll create 100 new, approximated features. Think of it as creating 100 new summaries from the original 5 features. The higher this number, the more detail I'll capture, but it will increase the computation time. The result of using SkewedChi2Sampler is 100 new, approximated features. These are my simplified representations of the original data, ready for use in whatever model I will use next. The main question is, how does changing the number of new features, that is, the _n_component's parameter, affect the quality and performance of this approximation process? If I increase the number of components, it'll get more accurate, as I capture more of the original data's information. However, it will take longer and require more computing power. It's a trade-off between accuracy and efficiency. This statement suggests that the new 100 features are unrelated to each other. That's not necessarily true. The SkewedChi2Sampler doesn't guarantee this feature independence. They're likely related because they are all generated from the same original data. This statement claims that the tool automatically handles features of very different scales. That's not quite right. While SkewedChi2Sampler is somewhat robust to skewed data, it does not automatically adjust for different scales. I usually need to standardize or scale my features beforehand for best results. This is a false statement. This approximation method, by definition, will not recreate the original data perfectly. There will always be some information loss. It's an approximation, not a perfect copy. I'm using Sklearn's kernelapproximation tool with the SkewedChi2Sampler to approximate a kernel's feature map. Think of it like creating a simplified, faster version of a complex mathematical function. I have a dataset with 1,000 different data points, each described by 5 different characteristics or features. I'm using the SkewedChi2Sampler, which is great for datasets with unevenly distributed data, to create 100 new features from the original 5. The "n_components" parameter, set to 100, determines the number of new features it will create. The result of this process is 100 new features that approximate the original dataset's structure. These features represent a simplified version of the original data which is computationally more efficient. This is the core question of the quiz. I need to evaluate the truthfulness of different statements related to the impact of increasing "n_components" using the SkewedChi2Sampler on the generated features. I'm basically evaluating the pros and cons of using more components.